Okay, good morning, everyone. Welcome back. So this is I hope you had a good, restful night. And this is the second talk of my lectures. And today I'm going to switch topics and I'm going to talk about learning equilibria in multi-agent systems. And I realized that I think in the week I think there are not many any lectures on multi-agent systems yet, so I will start with doing a little bit of a review of what is an equilibrium, and I'll talk about some of the approaches we can use for what are some of the challenges compared to single-agent systems, and what are some approaches we can use. Okay, so example of multi-agent systems, in driving, we have many scenarios where cars have to make decisions based on interaction with the other cars. These are pictures from a simulation, autonomous driving simulation environment. And in the lab, we also have these cars that we try to test our algorithms. In electricity markets, we have multiple players, like so producers and consumers, and they're deciding how much energy to consume and to produce, and they make profit or losses based on that. So there's also, they usually in these electricity markets, they run an auction and players submit bids for their production amount for a given price, and then the auctioneer, the market operator, gives them a payment and tells them how much to produce. So this is the amount of profit they make depends on the other agents' decisions. Similarly, okay, in the lab, I told you briefly, we also try to do multi-agent robotics and use robots to coordinate with each other and do build structures, for example. So in all of these systems, what we see is that we have a number of agents. So N agents, and agent I has her action AI, and the joint action here I'm showing with boldface A, which is action of agent I, and action of all the other agents is shown by A negative I. And each agent has an objective, Ji, that depends not only on her action, but the action of other players. And so this makes a problem. This makes the decision-making of agent I coupled with the other agents, because she cannot control her cost function by herself. Her cost depends also on others' costs. For example, travel times on the road depend on the routes that other players make, or the electricity bill depends on the total consumption. If the price of electricity depends on the total consumption and production, then the electricity bill also of each player also depends not only on her consumption, but the total consumption and production. And the problem that I've been interested for the past like maybe 8 years was, suppose that agents don't know these objectives, Ji, because this might depend in non-trivial way, like congestion in the road or electricity prices, on everyone's decisions. How could the agents, but the agents can make observations. So it's a learning setting again, so they can query their function, they can submit an action, and then others also submit an action, and they get an observation. How should they optimize their decisions? And so this is the overall question in the talk that we want to address. But first, I want to talk about what kind of notion of optimality we should look for. And the outline of the talk, I'm going to first start with static games. So when we don't have dynamics, and look at a class of games, convex games, where we have better understanding of how should agents optimize their decisions. And then we have also learning algorithms. And then I'm going to look at dynamic games and what we can do there. Okay. In a multi-agent setting, again, we can say that agent I's action set is AI, and we say that a joint strategy A star is equilibrium if each player is minimizing her costs given actions of the other. So A star I is the minimum of Ji given others have fixed their action and A star negative I. So it means that it's an equilibrium in the sense that no agent has incentive to unilaterally deviate from this decision, this choice. Okay. As an example, in traffic in an intersection, we have two players come, and if if one of them stops and the other goes, if both of them go, this is not an equilibrium because they get into an accident, they have a high cost. And if both of them stop, also not an equilibrium because they don't make progress. And if one of them stops and the other goes, this could be an equilibrium. And so here we see even, so the actions are just stop and go, and there are two players. And we can have already in this simple setting two equilibria. Yes? Yeah.
I'm picking the best option is less than the cost option.
Yes.
Different option. Are we just assuming that the other agents are picking the optimal option, or do we?
This is a definition of the equilibrium. So we say and joint strategy is equilibrium if no agent has incentive to unilaterally deviate, okay? So that's how we define it. So it should, for each agent, given others, it should be picking her best action, okay? And it's a equilibrium definition for in a non-cooperative setting, so we're assuming that we cannot influence other players' action or we cannot maybe communicate with them, okay? So then we just say that unilaterally I should be doing an optimal action. And it took, I think it took several years for people to come up to what is a good notion of decision making in these settings. From what's the notion of rationality and what shouldn't the players not do in a multi-agent setting. For example, they shouldn't play actions that are dominated and so on until it lead to this equilibrium notion. Okay. So Nash, okay, what are some in general? So the Nash equilibria may not exist, so maybe we can think of this like this simple game that you can think of rock, paper, scissors. You can try to play it with your colleagues. So this is, by the way, I actually have a course on game theory this semester, and we try to play some games also. So if you just think of this rock, paper, scissors, you're in two-player, and each player has three actions. And we can define a cost of 1 if the player loses and -1 for winning. So we call this a zero-sum game, and a zero cost if it's a draw. And we can see that this one doesn't have an equilibrium. Imagine you play rock and your friend plays scissors, then the one who played scissors thinks that I could unilaterally deviate. If I played paper, I would have been better off. And then similarly, like for every action, one of the players have incentive to unilaterally deviate, okay? So we don't have an equilibrium. So also just like usually in these finite action games, we represent them with this matrix where one of the players chooses the rows and the other chooses the column, and then we write the outcome of the game. So if, for example, a rock would be a draw and each player gets 0, and if one player chooses rock and the other paper, rock loses, so gets a cost of 1, and the other one gets a cost of -1, wins. And anyhow, this is a zero-sum game, so you can also just represent it with one number here. But this is the representation we have. But you can then, by just looking at these, if you pick any element here, you see that each player, for example, here for the paper, the column player would say, oh, had I chosen scissors, I would get a lower cost. I would get -1, so I have incentive to deviate from choice of rock column to scissor column, and so on. So there is no Nash equilibrium. There is other examples. I just put them in the slide, but maybe don't go through all of them, but you can work them out. This is an example. It's called the Bertrand competition. It's one of the old examples. And so the previous one, the players' actions were finite. They just had finitely many actions. In this case, the players are choosing their cost for a product that they're producing. Oh, I said, I guess here electricity. So let's say that their cost is AI. So player has to choose what cost they would choose, charge the consumer. And then they have a production marginal cost of C. So for every unit that they produce, it costs them C, and they can decide how much to charge the consumer. But let's say there is 1 unit demand, and the demand chooses producer with lowest cost, okay? And if the producer choose the same cost, then the demand divides. Half of the demand goes to producer 1 and the other goes to producer 2. And then here we can also look at the Nash equilibria in a couple of cases. If we have no capacity limit by each producer, and if each producer has a capacity limit, and you can write the cost function of each player. In this case, I think I'm writing the profit, so you can imagine maximizing the profit. So if player 1 sets a price lower than player 2, he gets the entire unit demand, so he will make A1 minus C, and if it sets equal to the second one, he gets half of the demand, and if it's greater than the price the second player chooses, he would get 0. Similarly, you can do the cost of player 2, and you can verify that choosing marginal cost as the price would be a Nash equilibrium, okay? Because if anything lower for any player would give him a negative profit, and anything higher would also give all the demand will go to the other producer, okay? So this you can argue it's a Nash equilibrium. Once we put capacity limits, though, we can work it out, but it will, the conclusion is that we will not have a Nash equilibrium. The player have incentive to keep raising their price because there is a capacity limit and the player cannot meet entire demand, okay? So there's just example, even if action spaces were continuous, we may not have Nash equilibrium. And for this, we try to restrict a class of games. And I'm going to look at a class of games in this now that we call convex games. And that means that Ji is convex in AI. And it's continuous in the entire, so for any given A negative I, Ji is convex in AI and is continuous in the joint actions. And also the action set of each player is convex and compact. And there are many examples of these convex games. For example, if you look at the so-called mixed strategy extension of a finite action game, I will define it in a moment. That's an example of convex game. Also, we have used, or not just us, but many people have used these convex games to model, for example, travel times, if you model them as a convex function of congestion, or the price of electricity as if you model it as a linear function of the total demand, then you would get that the Ji's would be convex for each player if the Ji is the consumption cost of each player. Okay, let me just give you a little bit more intuition. If we go back to this rock, paper, scissors, the mixed strategy extension of this game, so or any finite action game, it means that you will your actions become probabilities of picking any of those finite actions you had. So probability of playing rock, paper, and scissors. So your action set of each player becomes a simplex, which is the set of probability distributions on this like R3, because we had 3 actions. And then if we write the cost of player 1 as the expected cost, expectation with respect to each player choosing probabilities, you get this bilinear form. So the cost of player 1 would be A1 transpose C, where C is this cost matrix we already defined, times A2. This is a probability vector for player 1 choosing the rock, choosing between rock, paper, and scissor. And this is a probability of player 2 choosing rock, paper, and scissor. And because it's zero-sum game, player 2's cost is negative of that. And you can see that it's convex because action sets are convex, and also here they're compact. And if you fix any other player's actions, the cost becomes linear. If I fix a player 2's action, cost for player 1 becomes linear in her actions, in her now new action space. And so it's a convex function. Okay, I'll just pause for a moment. Are there any questions? Okay. So it turns out that in convex games, we can show that Nash equilibrium always exists. And so that's good. We know that if you want to compute it or learn it, it's something that it exists. And the idea for any time you look at these existence proofs for equilibria in games is that you look at the so-called best response map. So we say that we define the Nash equilibrium. A star is a Nash equilibrium if each player is optimizing over her strategy space given other players fixed. Okay, so A star I is arg mean over AI of Ji of AI A star negative I. And based on that, we can define a best response map that takes a joint strategy and gives us the set of minimizers for each player of their respective cost functions. And so just by definition, A star is a Nash equilibrium if and only if A star is a fixed point of these best response map that we can define. And then there are several best response fixed point theorems that we can use this part for convex games. The one that would be convenient is this fixed point theorem, Kakutani's fixed point theorem, that helps us establish that this best response map will have a fixed point, and so we have a Nash equilibrium. Okay, so just a summary of here, we defined what's a multi-agent decision-making problem and what could be a notion of optimality they can look for as an equilibrium, and that also if we restrict the class of games, equilibria exist. And furthermore, in convex games, they're characterized by so-called variational inequality. So I also briefly review that. So it's, I think, a lot of new things, and please raise your hand if something, if some questions come up, because I think in the week so far, maybe you didn't look at these multi-agent problems. Okay. So then the next question is, we know they exist, but usually these fixed point theorems that prove existence, they don't give us a way to construct them. But in convex games, it turns out that A star, if you, and if the cost is differentiable for each player, we can stack together the gradient vectors of each player's cost function with respect to her own decision, and we get what's so-called a pseudo gradient, and this is M, and we can show, A star is a Nash equilibrium in this convex game if and only if M A star transpose A minus A star greater than or equal to 0 for every feasible action in the joint strategy space. Okay, so maybe just to get a little bit of intuition, suppose we don't have any constraints, and if you look at this inequality, it would imply that this pseudo gradient has to vanish, have to be equal to 0 at an equilibrium. So basically the gradient of each player's cost function with respect to her own decision variable, and this makes sense because we said that each player is optimizing her own cost function given action of others, and if the cost is convex and differentiable, that means that by first order optimality condition, that means that these gradients, local gradients, so gradient of JI with respect to AI should all vanish. And then once you have constraints, this again looks like first order optimality condition in convex optimization, right? It just says that, except that here we have a pseudo gradient, not a gradient. It just, in also convex optimization, we have a first order characterization of optimal points based on the gradient mapping transpose A minus A star, simply by using Taylor series expansion of the cost functions and using the convexity to argue that it's necessary and sufficient that this inequality holds for every action. So this just extends those results we know about convex optimization to convex games, and the only difference is that here we have we are creating a vector field that's not a gradient vector field generally, because it's stacking together gradients of different objective functions. Okay, are there any questions so far? All right, so okay, you can look at a different game. Maybe it's also to gain a little bit of more intuition. This is called the Cornell competition. And now, in contrast to the Bertrand competition, the players are now choosing the quantity to produce, not the price to set, okay? And the price is assumed to be some linear model of total quantity produced, okay? So if players are choosing how much to produce, and they have still the same marginal cost, and there's a market price, and that's assumed that it decreases the more production there is. So it's some linear function, D and B are some constants of total production, and then each production has some capacity, each producer has some capacity constraint. And then if we write the profits of each player, we get the following, and you see that C, B, D, and are constants, and you see that this is a quadratic function in I'm writing the losses, sorry. So because this is the cost of production. So it's quadratic in AI. It's convex quadratic because you get that something plus B AI squared, okay, for each player's action, and B is a positive constant. So we get that Ji is continuous in A1 and A2 and is convex in AI. And the strategy sets are convex and compact. And we can also gain intuition a little bit about the pseudo gradient. So if we differentiate Ji with respect to AI, we just get a affine function of A1 and A2. And the Nash equilibrium, this is just a definition. We're just spelling it out for this instance, okay? So this is a convex game. And you can derive it as pseudo gradients by driving the local gradients of the players. And we can also try to solve this inequality. Okay, questions? Okay, so now I come back to the problem that we're interested in, and we want to look at learning in convex games. And so we consider, let's consider this is like the gradient descent type, extension of gradient descent. So let's consider, the so-called independent, because each player is updating her strategy based on her own local gradient. So AI at t+1, and it's a projected gradient descent. It's projection on the action set of player I of AIT minus some step size gradient with respect to AI of JI of AIT, A negative IT. And player I has to estimate that gradient because we said we're in a learning setting and they may not know their cost function, okay? So we call this an independent learning approach because each player is just updating her own strategy. She just needs to know her own action set and her own local gradient. And so a couple of things that I think for the next few minutes I want to focus on is what is the challenge if we kind of stack these together and every player does this, what's the challenge compared to a single player optimization, and how we can overcome those. So that's what I want to highlight now. So one challenge is that, okay, players need to estimate these local gradients, but they don't know the action of everybody else, and this function depends on action of everybody else. They only can control their own action. And then the second question or challenge is the convexity of Ji in AI sufficient for convergence? And we will see that it is. So the first challenge we discuss on how to resolve it, and in the second case we also see that local convexity is not enough for convergence of these algorithms, okay? And we will see what kind of conditions, what sufficient conditions we would need. Okay, questions about the setup? Okay, so maybe I think I'll first focus on this one. So how do the players estimate this? So you can think of this like gradient descent without gradients, but also without having control over the full parameter of the function. And what's the challenge? So normally in zero-order optimization, where we may not know the function or it might be too expensive to evaluate, we might use finite differences to estimate the gradients. So we can say that gradient with respect to AI, we just query our function at AI and AI plus delta, and then we divide that by delta, and we have this is just a finite difference, right? We can estimate that. But in a multi-agent setting, the challenge is that player, when she queries her function, she cannot ensure the other players are keeping their actions fixed, okay? So if the cost goes down after I go from AI to AI plus delta, it might be that the other players have chosen a different action, okay? Yeah. No, I'm not assuming so we're just here assuming they don't see other agents' actions or cost. They only see their own cost. Yeah, they're cost dependent, but they only see an evaluation of it. Yes, so it's a black box setting, yes. But it's a local black box setting. So the costs, I mean, each player sees sees her own cost function. Yeah. Yeah. Good. Other question? No, now that I call, we will see that we would need some randomization. Yeah. Good. Other questions? Okay. So this is a challenge of gradient estimation, like in this case where we cannot control the other players' actions because they might change their actions. So finite difference doesn't work unless we can coordinate everybody to, when I query twice, I should coordinate others to stay with their actions. Okay. And so for this, but this, again, we looked at zero order optimization literature, and there is also work there about in case you can evaluate your function only once, how can you estimate the gradient? And this is the idea of introducing some randomization. So it seems a little bit magical, but so what should the player do? The player should randomize her strategies, meaning that she should draw a random number from, let's say, for example, a Gaussian distribution with a mean 0 and variance sigma squared. And if she queries this function once only with AI plus delta, their delta is from this distribution, it happens that on average, by properly scaling what she obtained, she gets an approximation of her local cost function. Okay, and this goes to work of many people who look at stochastic optimization, and you can also, this is why when I say it's approximate, you can also characterize the bias and variance of this approximator. Okay, and this follows from by just by introducing this noise, and when you take the expectation with respect to this delta being from, for example, in this case, Gaussian, you get an approximation of the gradient of, you get the gradient of a smooth version of the function, which means the function integrated with respect to this distribution where the actions are from this distribution, and then you can relate that to the gradient of the original function. Yeah.
To clarify, so if they rent as queries, is that each agent?
Yes. 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 Yes, exactly. So each time they would draw their own, at each time step, they would draw some delta, each agent, and then they query their functions at AI plus delta. Yeah? Yeah. It's only fixed, each agent, so all of them, let's say that at each time, each agent has an action, wants to estimate gradient at their, evaluated at A, and they would query their action AI plus delta I, and then they scale their observation by delta over sigma, and this gives them an approximation of the gradient. Yeah, it's not, they don't control the other agents, actions. Yeah.
There'd be an expectation over all the actions of the other.
An
average across all.
Yes, because this depends on, yes.
Average over all possible actions.
No, sorry, this is just expectation over the delta being from this distribution, and each agent does this. Because this is actually an optimization result. It's not even a game result. If you want to use one query to estimate the gradients, you query this with a randomized, and then on average, and this is whether it doesn't have to be Gaussian, it can be uniform distribution, but on average, you get an estimation of your gradient at that. For one parameter, at A negative I, and each one of them would do that. For the function evaluated at Ji of A, where each one is choosing this their own AI plus the nodes. Yeah.
The others are at every evaluation of AI plus delta, if every other agent is choosing a random action.
They're choosing their own AI plus delta. Yes.
Then you take an expectation, then specific for one AI minus A minus.
Maybe so each agent would get an estimate of this one, like evaluate at here.
I thought there should be. I'm not from this background, so I'm completely as a beginner asked. Won't there be then an expectation over A? No, but because it's A minus I, so it does depend on I. So yeah, I don't still get the intuition for why, because it's not for one specific action of the agent. So we.
I'm just trying to see. Okay, maybe you can look at it and yes, and me too. I think this probably I can explain this like better, or maybe have more slides about this in future, because I think
That for a given action AI, the actions of all the other agents can be anything, and within that set of anything, we need to take an expectation.
But I'm just estimating the local gradient evaluated at AI, a negative I. I think I don't quite see it, but maybe we can look at it again. Yeah, thanks. We can talk again after. I didn't quite see why I need to do that, but let me just think, going through the steps.
So basically, I'm saying there's extra noise apart from delta. That noise is coming from the other agents doing all kinds of actions. And not just delta perturbations on their actions, but completely different actions. So there's this extra noise coming from all the other agents doing different things. And so that noise somehow doesn't seem to come in here. So I would imagine there's an expectation over that.
Okay. I think it's not obvious to me, but maybe we can look at it later. Yeah. Thanks. Yeah, yes, we can look at it later. Okay. Then, okay, so with 1-point query with introducing noise, you can have an estimate of the gradients. Yeah. No, we don't assume AI can observe A minus I. Agent I can observe A minus I. If we observe, so we assume we don't know JI, okay? And we also don't observe others' actions. Yeah. You can it turns out you can approximate the gradient, and it's again, this is not a game thing. It even goes to this bandit optimization literature. If you have a and there, you have a time varying, even a time varying cost function of single player, and the question was, how can we estimate the gradients of these? Because the function at the next time step, it changes. And there they introduced this idea of randomization. It turns out that it works there. Yeah, but we can maybe, depending on time, we can look at it a little bit more at the papers. I can exactly also cite you or write the equations. But they don't need to observe other players' action. It's from agent I's perspective, this could be a time-varying function, okay? Because she cannot control the other's actions, and she cannot observe them.
Then you then get the gradient at a specific time?
At just that time. Yeah, you're just estimating the gradient at that time. You're not trying to learn that gradient function or the original cost function. Only at that specific time, yeah. Okay, yes, I think it's maybe not so obvious, but we can discuss later. Okay, so now the second challenge was here, if we just stack together all players update rule, and I drop the projection to simplify, and I even have these, the exact accurate ones. We want to see what's the challenge with this gradient descent update. And what you get when you stack each player's update rule, you get this pseudo gradient. So a at t plus 1 is equal to, like the boldface a t minus a times some pseudo gradient. And this is not generally a gradient mapping. An example, if you have a zero-sum game, this is a very simple zero-sum game. Player 1 is minimizing with respect to a1. This cost function, player 2 is maximizing. And if you stack the pseudo gradients, this is the linear mapping that you get. And this is not a gradient mapping, because for the gradient mapping, this matrix had to be symmetric, because this is partial of J1. J would be partial of some function with respect to A1, A2, and then here A2, A1, and it would be the same for a single function, okay? So this is not a gradient mapping, and generally single agent analysis, which they rely on saying that one objective function is decreasing over the iterates of gradient descent, that kind of analysis doesn't work, okay? So I just pause and see if there are questions about this. So we're going to see, and as you can imagine, we would need some conditions on the pseudo gradient to be able to say whether this iteration converges or not. But this looks like dynamical system that we know how to analyze. We want to see, and we see that the equilibrium of the system is actually our Nash equilibrium, because MA of t would be 0. And if we have projection, again, we can show that the equilibrium of this system would be the Nash equilibrium. So we know that the properties of MAT can tell us whether this algorithm will converge or not. And the property we need for, or sufficient properties we would need, are based on the so-called monotonicity of this pseudo gradient. So we call this mapping monotone. If the following inner product is always greater than or equal to 0, and strictly monotone is always strictly greater than 0 and strongly monotone, if it's greater than or equal to this new times norm difference between A minus A prime, okay? And you see that it's exactly, if this was a gradient mapping, this would be exactly like the definition of convexity, strict convexity, and a strong convexity. It's just generalizing these definitions to a case where this is not a gradient mapping, okay? And similar to convexity, you can also, if you have differentiable mapping, you can just look at the positive definiteness of this Jacobian of this M and determine whether the pseudo gradient is monotone or strictly monotone or strongly monotone. And there are some classes of games which we call potential games, where it turns out that this Jacobian is symmetric, and so this means that the gradient mapping corresponds to gradient of a single function, and this then reduces to optimization problem. Okay, are there any questions about this? Okay, so these conditions, if we have these, I think here is also a couple of examples, like in the rock, paper, scissors. If you look at the cost of each player in mixed strategies, which was this bilinear form, and if you form the pseudo gradient mapping, you can verify that it's monotone, but not strictly monotone. And in the Cornell game, you can also show that we have a strongly monotone, and also in this case, symmetric Jacobian pseudo gradient. Okay, so there are many classes of functions that, many classes of games that satisfy this monotonicity property. Okay. So when putting this together, now here, let's say this was our independent learning algorithm, and we stacked them together, and they estimated this gradient with this 1-point query. And then if we have sufficient conditions for convergence, if M is Lipschitz and strictly monotone, then if we choose the step sizes, so that the step size is not summable, but we balance it with the variance, then this AT converges to the A star almost surely. And this is basically extending results in zero order or in stochastic optimization to a game setting where this is not a gradient mapping, but actually the proof is very similar as well. So you would look at the difference. So we don't have a single cost function, so we cannot talk about the decrease of the cost along the trajectory, but we can talk about the distance of AT plus 1 minus A star in expectation along the trajectory of the algorithm, and then we can write that as less than or equal to the previous distance plus some term that becomes summable, and then plus some term that from monotonicity, it follows that it's greater than strict monotonicity. It's sufficient to say that this is greater than zero, and then we just use existing results about convergence of random sequences to argue that with these properties of this inequality, with these remainder properties, this sequence will be converging. Okay. So, okay, just then the summary is that we can have an independent learning algorithm that players don't need to see others' actions, or they don't need to know the cost functions, but they can do a local estimation of their gradients and update their actions. And then based on these conditions, these are sufficient conditions for the pseudo gradient mapping, we would have convergence. Okay, and over the past years, there's also many extensions to relaxing, for example, this strict or strong monotonicity for convergence. For example, looking at games that are, their gradient mapping is merely monotone, such as convex concave zero-sum games. Games that have coupling constraints. In this case, agents had their own action space constraints, but their actions might be coupled. And then games that even don't have monotonicity, but they have equilibria that have nice properties, okay? But then many games, such as these dynamic games that we look at, don't generally satisfy these conditions. So for the rest of the talk, I want to talk a little bit about what are some things you can do in dynamic games. Are there any questions so far? Okay, so then again, so we looked at stochastic local gradient descent for players to learn equilibria, and we see a lot of connections with convex optimization, but small differences. But there were conditions on the game map that we could derive that we could have convergence. Okay, and now let's look at the dynamic setting, and this relates more with the RL and control part, but I wanted to first start with the static games, because when I first started working on game theory, I realized, okay, we have to start from static games to understand them before we can move on to dynamic games. So, okay, now we're going to talk about the dynamic game setting. So here, we say that we have a state S at time h plus 1 is a sample from some probability distribution. This is just an extension of the stochastic control framework. It's a function of SH and the actions of all the players, A1H to ANH. Okay, so the only difference is now instead of a single controller, we have all these players choosing actions. And this is the initial distribution. And each player has a policy, which is a map from the state space to, so I'm starting with, again, finite state and actions, let's say, games. So to define this, so to a probability simplex on her actions, okay? So a randomized policy. And then the cost of player I depends not just on her policy, but the policies of all the other players. This is just like a stochastic control cost. Just that my notation changed a little bit. Now this is a discount factor alpha to the h it should be, so I had to, sorry for that, I changed back the notations between the two talks. So now here I have h, because I had t as iterations of my algorithm, as the time, and this is a discount factor, and this is a cost of player I that depends on the state and the policies of all the players. And then we say we have a Nash equilibrium policy. It's actually the same definition as before. No player has incentive to unilaterally deviate from her own policy. Okay. And we started with this finite state and action setting because there we know that Nash equilibria exist, and this goes back to the work of Shapley, where he first formulated this for zero-sum Markov games, and there they call it actually stochastic games. Well, they in the math literature, when they talk about stochastic games, it's what we call Markov game, basically a dynamical system. And then it was extended from zero-sum to non-zero-sum games in the subsequent works. Okay, in the continuous state and action setting, we don't have general conditions for existence of Nash equilibria, but I'll discuss that briefly a little bit as well. And then now we are in this reinforcement learning setting that we say that, just like yesterday, let's parameterize the policy with some parameter, but each player has their own parameter, theta I, and we want to find equilibrium, and now the problem gets cast as finding the set of parameters that these policies, resulting policies, would be equilibrium policies through interacting with the systems, okay? So this would be the kind of the reinforcement learning setting we had yesterday, but in a multiplayer setting. Okay, let's pause. Are there any questions about the setup? All right, so now we're gonna look at what are some of the challenges. So here, like yesterday, we looked at single agent. That's when we looked at the gradient descent type approach. So policy gradient, theta t plus 1 equals theta t minus some a dot t times gradient of theta j of theta t. In a multi-agent setting, it actually becomes, this policy gradient becomes exactly like what I talked about so far with the static games, because now our decision variable becomes finite dimensional, and it's just like stacking together each player's update rule, okay? And even though in policy gradients, we know that they are convergent under some conditions, such as Fisher non-degeneracy and so on, there of the policy parameterization, we have convergence conditions. It's well understood in the RL literature by now. In a multi-agent setting, generally these algorithms, extending it to the multi-agent setting, generally they're non-convergent, okay? And based on what we talked earlier this morning, what we can think about is once we stack these gradients together, we don't have generally any monotonicity. It would be very hard to show with, or I don't know examples of games that, unless it's a single state game, that you would have this monotonicity. But I also want to bring attention to the one subclass, linear quadratic games, because we're in control. We like to look at linear quadratic games a lot. And here, policy gradient algorithms, for example, which means that you parameterize your linear policy with theta, and then you use gradient descent to learn this theta. And we know there exists work that show that this policy gradient would be globally convergent. And as soon as you look at the multi-agent setting, which is a linear quadratic game, so each player has their own objective functions, but the dynamics is controlled by action of all the players. And then you try to do policy gradient exactly like the algorithm I showed in the previous slide. So like this, by stacking these together, so each player is updating their own linear policy. They're generally they don't, so far, generally for this infinite horizon setting, we don't have any provable convergence, even in the linear quadratic setting. And we tried to look at it a little bit with one of my students to understand a little bit more about this. And we looked at two-player infinite horizon LQ game, even a scalar setting. And there you can show that Nash equilibria are a subset of solution set of a third-degree polynomial in two variables. And you can kind of argue with using some algebraic geometry tools that there is at least one, at most three equilibria, and basically you don't have unique equilibria in these linear quadratic games, and it's very hard, even in the scalar setting, to derive anything about uniqueness, monotonicity of the equilibria, or whether there exists some potential function of the game. And as you change the game parameters, this is showing the number of equilibria that are changing from 1 to 3. So we don't have uniqueness conditions or equilibria, and it's very hard to understand the properties of this pseudo-gradient mapping when we put them together. But there has been some work that show convergence conditions for subclasses of Markov games. For example, finite horizon linear quadratic games, there's been some results. In finite state and action potential games, and in zero-sum Markov games, there's been some results about convergent algorithms, convergent reinforcement learning algorithms. And for more general classes from, we know that provably computation or learning of Nash equilibria is intractable. Just make pause. Are there any questions? Okay, so because of that, we're gonna now look at what, okay, if we know that provably for other general class of games, computation and learning of equilibria is intractable, maybe we can relax the notion of equilibrium that we look for. And so we're gonna look at a relaxed notion of equilibrium. And this, the one we call, we look at is called a coarse correlated equilibrium. Okay, so now we call, so before we looked at mixed strategy equilibria where each player randomized chose a probability over her finite actions. Now in a coarse correlated equilibrium, we also have randomization, but this is a probability distribution on the joint action sets of all the players. So this P star is a probability distribution such that if you sample a joint set of actions from P star, so parameters from P star, then no player has incentive to unilaterally change their action. Okay, in this traffic light example, this is a classical one that's used when people teach coarse correlated equilibria. We talked about two equilibria, one which were either car A is stopping and car B going, or car B stopping and car A going. And both of these equilibria, these are determined, there's no probability distribution here. And in a coarse correlated equilibrium, there could be a traffic light that based on some probability distribution chooses to show a green for B or show a green for A. So it gives a signal to both of them, and this is a distribution on the joint set of actions, okay? So that would be a correlated equilibrium, coarse correlated equilibrium here. And there are some results, there are existing results that show that if you have a no-regret learning algorithm, which yesterday you saw a little bit in the lecture, not my lecture, there was lecture, they converge to a coarse correlated equilibrium. And our goal it would be now for the remainder of the talk is to how to have a scalable no-regret algorithm first in the non-dynamic case, and then in the dynamic case. Okay, so we said learning Nash equilibria can be very hard if you don't have any monotonicity conditions, and we said let's relax the notion of equilibrium. And with this notion of equilibrium, we know that there are independent learning algorithms, the so-called class of no-regret algorithms that have provable convergence to this notion of equilibrium. So it's a bigger I don't know. It's a bigger set of equilibria, so we are relaxing some performance, perhaps, of our system, but it's computable and in a almost a scalable way. And then I will a little bit review also this no-regret algorithms, which you saw yesterday as well. Okay. So what is this no-regret benchmark, and what's this no-regret setting? So let's now say that we just look at player I's perspective, and suppose that she chooses some action theta t at time t, and then she has a black box. She doesn't know what the cost function is, but she experiences a cost ji of t theta t. And then based on just these observations that of this cost, and she wants to update theta. And the regret of this player is defined as the difference between her incurred cost for the choices she made and the best cost in hindsight. So had she known these functions and would take the summation and take the best fixed action, this would be called, the difference would be the regret, okay? And we say an algorithm is no regret if this RIT on time average goes to 0, okay? So this comes from the learning community, the adversarial learning literature, where they don't have actually a game setting, but they have a sequence of time varying functions and players are interacting with that. In our game setting, this framework exactly fits, because even though player's cost function is not dynamic because she cannot control the actions of others, practically she's seeing a dynamic function because other players are changing their actions. Okay. Let me see. Yeah, so this is exactly what I said. In the ji of t here in our game is ji, the static cost, but because of the time variation of others' actions, player I sees a time varying function. All right. So then, yeah, this is also the result that I referred to. If each player is implementing a no-regret algorithm, the empirical distribution of the played actions converge to a course-correlated equilibrium. And in some subclasses of games, such as zero-sum games, they actually converge to a Nash equilibrium. So there we have a stronger result. And furthermore, we can directly map the regret rate to the rate of convergence to an approximate course-correlated equilibrium. So this is the connection of no-regret learning and multi-agent learning. So no-regret players doing no-regret locally based on their observed cost, the joint action profiles, the probability distribution, the empirical distribution would be a course correlated equilibrium. Yeah. No, not necessarily. Huh? You could have? You could, sorry. Given that others are also choosing equilibrium. But this is the cumulative cost and it's not the one instance cost. Yeah. Okay. Yes, you can understand it as cumulated best response dynamics for accumulated cost. Yeah. So now we just say each player can do her own no regret algorithm, and if all of them do their own no regret algorithms, then we have this convergence. They can achieve. So this is. Yeah, there is results that design, like, again, coming from the learning literature and adversarial bandit literature, that because this is exactly a setting of, it's a more general setting than a game. It just says you're observing a sequence of time varying functions. Okay, in our game, these turn out to be these functions evaluated at theta negative I of t. Okay, so if you use the standard, which I will briefly talk about, the standard result from, so if you forget about this I and you think of this as one player seeing a sequence of time varying functions, there exist no regret algorithms under, you would have to assume these costs are bounded, and if if the player has n number of actions and there are t number of iterations of the algorithm, so there is the best known algorithms, their regret grows as square root of t and log of n. So when you take the average divide by t, it would be converging to 0. And then also, if this is the case, the players do not see they do not see these time varying functions. But if they do see at each instance what is that function at that instance of time, so they not only they see ji of t evaluated at theta t, but they see ji of t evaluated at any theta they could have chosen, then the regret grows as root t log n. Okay, because you can imagine that we have as if n bits more pieces of information because we're seeing the function for every choice of action we could have made. Yeah.
Summation the best loss, summation of losses over p is this, for example, something about that
Not really, not quite. Yeah, so, or I don't. I have because now we don't have a dynamic game. We even have a static game. We don't have a game tree or a dynamic game. So we're just looking at a static game, but it's a repeated static game. That's a good question. You can imagine it as a static game that's being repeatedly played. I again went back to explain the concepts in a static setting because also we parameterize our policies with some finite parameter and we reduce the dynamic setting to a static setting. Yeah. Okay, good. Other questions? So the players are repeatedly playing the same game and observing the same, their cost functions evaluated at different choices of actions. And then reinforcement learning would be that they play a policy and they observe the trajectory, and from that they estimate their J's, their cost functions. So this doesn't even converge to Nash equilibrium. So all it says is that this approach would converge to a relaxed notion of equilibrium. In zero-sum games, it would go to a Nash equilibrium, but in zero-sum games, the Nash equilibria all have the same value. But yeah, that's a good question because here this is a bigger set and some equilibria might be better in terms of some efficiency metric, but it doesn't say which one it goes to. But there are some results that bound the so-called price of anarchy of the equilibrium, depending on the game structure. Other questions? Okay. So this, we know no regret algorithms exist, and we know this, they have this rate. And so this was the starting point of the work of my former PhD students, Pierre Giuseppe Sessa, where the idea was, okay, we have this n scaling in n is really bad because if our action comes from discretizing a continuous domain, this will be a very large number. And so we wanted to try to improve, basically try to bring these rates, right, of banded learning, meaning if you're not observing the cost, to this rate of full information setting. But there are some theoretical lower ones that say that in the banded setting, actually, this is the best rate you can achieve. So generally, we cannot do that, but we made some additional assumptions, which I'll talk about now. Okay. Yeah, so that's what we started to look at. I think I had I shortened my slides, but hopefully I still can. I shortened my slides, but hopefully I can still communicate our approach. Let me just check. Okay, it's very condensed, but I can talk about the approach. So has anybody seen the approaches for doing these no-regret algorithms, for deriving these no-regret algorithms in a single player setting? So there are a class of algorithms that are called multiplicative weight update. And these approaches, basically, they start by putting some weights on the different actions, okay? And then based on the experience costs, they update these weights, okay? So this is called the class of multiplicative weight update algorithms. And so intuitively, I will explain it to you. So let's say you have this WT is a distribution. WT is a weight of actions A1 to AN, okay? And so you update these weights based on the observations we make. So Ji of, by choosing a given WT, you sample from this distribution, and then you play that action sampled from this distribution. And by observing this cost, then you update these weights. And this class of algorithms, actually, by properly updating these weights, and the algorithm is called multiplicative weight update, because WT gets updated in a multiplicative way based WT plus 1 as a function of WT. And by using this information, they update it. And by optimally choosing the weight update rule, they make sure that the algorithm has such a regret. And what we try to do in the banded feedback, they only use 1 point information, so they can only update weight of one action, okay? In the full feedback, they observe the cost for any action, and they can simultaneously update the weight of all the actions. And we try to mimic this full information by saying, suppose the function, we learn the function by interacting with the system. So if we learn the function, then we can evaluate the function for every chosen action and update the rules. So I give you the high-level idea now applied to the Markov setting, but the work build on our work first in the static setting. Yeah. Yeah, there are probability distributions, exactly. Yeah. Yeah, so here the actions are, let's say they are finite. And WT plus 1 would be some proportional to WT and some exponential function of the experienced cost. Okay. This is the update rule, and then beta is chosen somehow suitably, and this is where the experience comes into play, the experience evolve. Okay. Okay, I think it's a bit condensed, but hopefully I give a bit of a high-level idea of what we did once we extended the work to the Markov game setting. Now here, so we parameter, or my student looked at the case where here was our dynamics, and we said that, okay, if we can learn the dynamics somehow, then we can learn these objective functions. And then instead of just updating the weight intuitively, you can think of it like this, but the algorithm is more involved. Of one action, we can simultaneously update the weight of several actions. So we will get a full feedback. We will mimic full feedback because we learned the functions. So we model this F by a so-called Gaussian process, which maybe you saw in this week. No, okay. So I think I saw in some of the lectures they will talk about this topic, but maybe I missed that. Anyhow, so it's a model-based approach when we try to use the data to estimate the functions F, and from that the objective functions. This is just what this says is that F is some sample from a probability distribution on the functions, and it has a mean and a covariance. So these could be all the functions before we have any measurements, before any prior information. And then once we make some measurements, we can update the mean and variance based on past data using something like a linear regression. And you can have different kernels for these Gaussian processes. So you can have a polynomial kernel or exponential kernel and so on. And based on this, you can then use the observations to update the function. And wherever you made observations, your uncertainty about this function decreases, and also about the neighborhood of the points you made measurements. Okay. But all it's saying is that it's a model-based approach. We try to estimate the functions. Yes. Yeah, I think I just I switched a little bit. So this was a finite static game, finite action setting, and first we looked at that to understand how do these algorithms work, and we find that they have some multiplicative weight update, and the way the weight is updated is in the bandit setting, it only updates one of the weights. In the full feedback, it updates all of the weights because it observes this function for every possible action. So if we learn these functions based on data, then we could try to simultaneously update all the weights. That's the high-level intuition behind this algorithm. Okay. There's no W here. The F is the dynamics. We're trying to basically learn these functions. You can intuitively think of that. If you think of the original adversarial like bandit setting, here the player either observes the experience cost for any chosen action or experience cost for just the only for the chosen action or for any action she could have chosen. Okay, and if we can learn the functions, and we can do it in a game because it's actually a static function, then we could have a full feedback. That's the high level idea, but I skipped a few slides. I realized as I shortened, I shouldn't have done that, because first we actually extended this in a static game setting before going to the Markov game setting. But that is the intuition. Let's learn the functions so that we can mimic this setting even though we are only observing these actions. Okay. So now we are using the model-based approach for reinforcement learning to learn these functions from which we can learn the JIs. Okay. Oh, yeah, probably. Yes, I got it. Yeah, so this is just a Markov game setting with some noise. That's not that great. Yeah. Sorry about that. Okay. Okay, I think I skipped a lot of details, but maybe the high level is important because it indeed takes this was a 4-year work with my PhD student and collaborators on how to kind of extend these to be able to get better regret rates. And the last thing from a static, and the last result is in a Markov game setting. So here we are playing the policies. The players are getting they're observing the state of the game and the sequence of played actions. They estimate the dynamics, and then once you have the dynamics, you know that your J's, and you can compute equilibria, and then you update your probability distribution, and then you repeat this process, and then we have conditions on the function f that it comes from this Gaussian process. It has Lipschitz continuity. All of these functions are Lipschitz continuous, so your policy parameterization, the rewards, and f, and then we can bound the regret of this multi-agent reinforcement learning algorithm as a square root of t, it, but the point is that we don't have exponential dependence on the dimension of action space, so everything here is actually captured in this information gain, how much we can learn about the function, given that it comes from this modeling class, by making observations. And this one is sublinear for a lot of games, for a lot of kernels, and sublinear in the dimension of the state space and input space and number of players and the horizon of the game. Okay. It's the high level, but so the high level idea or the goal was, we started with saying that, okay, Nash equilibria are hard to learn. We're going to look at the subset of equilibria that can be learned by no regret learning. And then in no regret learning, we saw that existing results scale poorly with the number of, with the dimension of action space or the number of actions that each player had. So we try to use a model-based approach to reduce this dependence by learning the functions, by learning the cost functions from data. And then I think, so this was my PhD student, and I co-advised him with Andreas Krause, who is my colleague in computer science department, and who works a lot on these Gaussian processes, and this initiated this idea of bringing these tools to our setting. And I just end with an example so we can also get some intuition maybe how we could apply this. And so this was the example. I was fortunate to have the Pier Giuseppe as my student because he was both good in theory and he could make things work in actually really like in reinforcement learning simulation environment. So this is called SMART. It's actually a multi-agent reinforcement learning simulation environment from autonomous driving, and it uses actual like realistic car dynamics models and traffic data, all based on real data and real physics engine traffics. And it has a bunch of examples where cars have to coordinate with each other. It's a multi-agent setting, the decision making, like in this autonomous driving. And we try to test our algorithm in this setting. So here, just looking at one instance, so the objective, these are the cars, the autonomous cars. This is a human-driven car. It's a picture from this environment. So sorry that the resolution is not so great. So this is agent 0, agent 1. And this one wants to change lane to come to the lane of human-driven car. And so the dynamics are all the dynamics of all the cars, which we assume we don't know. It's a black box setting. So S is the position and velocities of the cars, and the actions of the players are actions of these autonomous cars, and which are heading and speed. And then the policy is parameterized by a neural network, which came in that simulation environment. We're just training that policy. And so what we aim to see is that if these agents, if we look at it as a single, if each of them looks at this as a single agent problem, they might be conservative because they see the other one as kind of an obstacle, and they don't take opportunity to coordinate. But if we look at it as a multi-agent setting, they would coordinate and together more likely overtake the human-driven car, both of them. And so that's what we find based on our we implemented this algorithm. And here was a single agent optimal. So these are the rewards for the agents, cumulative rewards for average over the agents, agent 0, agent 1. And this is if we use a multi-agent, if we use the multi-agent rather than a single agent approach, they have, so the reward was progress towards progress as fast as possible. They have slightly higher rewards. So this implies in practice exactly what we see, that when we look at it as a multi-agent problem, they coordinate more and they overtake the human-driven car more often. Whereas if you look at a single-agent problem, they break a lot and they might wait behind this and let this human car go first. And then Pierre Giuseppe also compared this with so this was our model-based approach, and he compared it with this model-free approach, which is called deep Q networks, and it came with that in that simulation environment. And what you see is that with a model-based approach, we need much less interactions with the simulator to get to a given reward. So in the model free, he cut this off. So it needs, here it needs about 30 interaction. There you need 15 or let's say 10,000 interactions to get to the same amount of reward. So the model-based approach appears to be more sample efficient here. Okay, I think that's end of the talk. So in the static case, I talked about banded learning of Nash equilibria, and we talked about the coupled learning algorithms, using players only using their own function evaluations. And in the Markov game setting, I motivated no-regret learning and presented some algorithms, some approaches to tractably learn force-correlated equilibria. Are there any questions so far? What is just I go to, yeah, so there's a lot of work that we are looking at. A lot of my group is looking at currently learning equilibrium Markov games under safety and reachability constraints. provable algorithms are under partial and asymmetric information, which is very challenging, but it's very relevant in multi-agent setting because each player might have their own observation, and learning of good equilibria, which relates to your question, because there might be different equilibria and they have different efficiency implications, and we also try to look at applications in different domains. So yeah, this talk, the main contributor for the second part was Pier Giuseppe, and for the first part, my colleague Tatiana Tatarenko, who is at TU Darmstadt, and then my student Pier Giuseppe looked at, Giulio is looking at linear quadratic games, and Andreas Krause, who worked with us on Gaussian process modeling. So yeah, thanks very much for your attention, and I'm happy to answer your questions more. Thank you. Yeah.
Only comment, I have to think about the game.
Yes.
In the optimization, I've done a lot of work on that.
Yes. Okay.
If you're, you avoid IoT noise,
Okay.
like something very correlated, get rid of that one, that's all. You can get better.
You can get better? Okay. Okay, that's interesting. Yeah, I see recently that people use history, so maybe it's similar idea. So, that's actually interesting. Okay, I love to. Because now the variance is 1/sigma², and that's a challenge. Yeah. Yeah. Thank you. Yeah. I can imagine because I can imagine because maybe it's like using history and some, no? No. Hmm. Okay. Okay. Thank you for the input. Happy to look at it. Yeah. Yeah.
I have a question on the settings, slide 20. Just what an example of an action and a disturbance would be in a static setting. So, yeah.
Sorry, what's the question?
An example of this AI action that we can take and the delta disturbance sort of that we introduced.
So in like think of the corno game. Corno game. The action, I think I have it as an example. And suppose that players don't know the other, how much they're playing a repeated corno game. They don't know the price function because now we just make assumption price is a linear function of total demand. We just don't know what it is, right? If they don't know the price functions, then they cannot know functional form of their profit. But they can play this repeatedly, or they can maybe use a simulator that has a price model. And so by choosing an action, AI, which would mean they choose some production quantity, but they perturb that with some noise. Okay, and my noise example was bad because it's Gaussian, which means that you could get an unbounded action, but actually in the technical work, we project that, okay? Or you can use from uniform. But it just means that if I look at my iterate, the iterate of my algorithm is AI is 5. Now I want to query it as at 5 plus some delta that comes from the Gaussian noise, for example. Does that make sense? So they play this corno game repeatedly. They update their actions based on this gradient, local gradient estimation, and that's how they estimate the gradients. Good question. Other questions? Okay, yeah.
Sorry, you mentioned the
About what? Sorry. Autonomous driving. Yes.
Talk about
Yeah. Yeah. We haven't applied in supply chain. That seems interesting. Yes, but I know some colleagues at ETH who looked at supply chain like from a game theoretic perspective. Yeah. other questions? Okay, if not, thank you. And I just, thanks a lot. Thank you.